diode and its application. First topic rather, because you have chapter 1 and chapter 2. Two topics are left. The first one is clamper and the other one is Zener diode. We kind of started the clamper near the end of our previous lecture. We'll go through the clamper again, maybe do a couple of examples, and then we'll move on to Zener diode. Just now, I have assigned homework assignment number 1 to you, which you can find on your Teams page. It is due next Tuesday, and you submit electronically. Send me preferably a PDF file here. You can submit here. I don't check all 38 assignments. I randomly pick maybe 20 or 30% of the class and look at their work. But I provide solutions for all. After the assignment is past due date, I'll provide the solution. So if you may have any questions, you can ask me. Excuse me, there's something in my mouth. I have a lozenge, my throat. I have a sore throat, so I might sound a bit funny. Hope that's okay. I'll turn off my camera and go directly to screen sharing. Okay, just looking for your lecture slide. Right here. I hope you can see my screen. Let's go directly to the page where we started the clamper. So when you have a diode clamper circuit, first thing you should notice that there are 3 elements. Immediately after the input, you will have a capacitor, and then followed by a diode, and the load will be represented by a resistor where you connect your voltmeter probe and then measure the output voltage at different half cycles. There are 5 steps of solving a clamper circuit. When you look at the circuit, first of all, see the input waveform and decide whether the diode is forward biased or reverse biased. So which part of the input signal will make the diode conduct. In this case is the positive half cycle, because the diode now is forward biased with respect to the input. You start your analysis with that half cycle. You take the loop, determine the output voltage, also determine the voltage and polarity of the capacitor. This is when the diode is on. Then you go to the next half cycle. When the diode is off, you have to assume the capacitor voltage and polarity that you determined during the on cycle remains the same. Same voltage, same polarity. Do the analysis for the off part. And then stage number 4, during all times, you have to maintain the awareness of voltage, polarity, and current direction. Do not make any mistake, do not mix things up. The last step is to check the total swing of the output versus the total swing of the input. In this example, you can see positive half cycle a swing of V, negative half cycle a swing of V in the minus direction. Total input swing is 2 times V, and the output swing total is 2 times V. I am ignoring the minus sign. The swing is taken by measuring the 2 extremes. What is the positive extreme, or what is the maximum extreme point, and what is the minimum extreme point? Once it is satisfied, you are done with your circuit. Now let's quickly look at this, and we will do an actual example from the textbook. Here the answer is kind of given. Can you see the bias clamper circuit with a 20 volt peak to 40 volt peak to peak input? Do you see that?
Yes, we can see it.
Okay, look at the circuit. during which half cycle the diode will be on. You see it is upside down, so we will start our analysis at the negative half cycle, because at the negative half cycle the diode will be on. So you can do like this, put a plus here and minus here, plus minus. In which direction the current will flow? It flows from plus to minus, so it is going to flow counterclockwise in this loop. When the current flows from right to left, the capacitor charging like this. The first conductor is plus, the second conductor is minus. First thing first, you determine what is the output during the negative half cycle. This is an ideal diode, so it's short, and you are measuring V out across these parallel nodes. What is your V out during the negative half cycle? It is, see the voltage 0 and minus 10. It is minus 10 volt during the negative half cycle. So you solved one part of the problem, and then look at the loop to establish VC. So I'll take from the outer sign VI minus 10 minus VC equals 0. Therefore, what is VC? VI is 20 for the negative half cycle. 20 with the plus sign here. 20 minus 10 minus VC equals 0. Therefore, VC is 10 volts, isn't it? The magnitude is 10, and notice the polarity. Drawing 0 is a bit tricky because of the autocorrect. See, it doesn't allow me to draw. One more time. Okay, 10 polarity is like this. Minus on the left hand side, plus on the right hand side. What is the next step? The next step is to find and analyze the other half cycle which does not forward bias the diode. In the other half cycle, what happens? This becomes plus and this is minus. The bottom one is minus. This is the positive half cycle now we are talking about. Bottom one is minus. The middle node is open, no current flows. So where is the current flowing? The outer loop is now a closed loop. It will flow clockwise. Use the KVL equation. VI, which is 20. 20 plus 10 minus VR, which is VR is same as V out. You can say minus V out. 20 plus 10 minus V out equals 0. Therefore, how much is V out? 30 volts. Here you have 30 volts during the positive half cycle. You see it starts when the input voltage is 0. What happens for VI? 0 plus 10 minus V out equals 0. Therefore, V out is 10. At input 0 volt, V out is actually starting at this point, 10 volts. So the exact curve is like this for the positive half cycle. So what have we solved? We have solved for the output voltage for both the negative half cycle and the positive half cycle. And now what? Check the total swing of the input and output. What is the total swing that you can see from the input waveform? How much is the total swing?
40 volts.
40 volt. 20 here, 20 here, from one extreme peak to the other. And then you have to see the total swing on the output side. 30 and 10, 40. So this is the correct answer. Your problem is now solved. If you want to see how the generic output from a clamper circuit would look like, this is from your textbook and also on this slide, which shows different clampers. Forward bias diode, reverse bias diode, with and without bias. Now let me quickly zoom in to one of these output waveforms. Say you have an output waveform like this one. how are you going to measure the swing? Sometimes the output does not go to the negative side, but I told you the swing is measured from one extreme to the other extreme. So this is the highest and this is the lowest point. The swing has to be measured from here to here. I think we will see one example now, shortly after this one. Any question about the clamper? Are there any questions? So let me bring you back, or rather bring you to a problem that I have prepared for you. This is a worked out example of chapter 2, example 2.22. And it is already worked out in the book, but we can do it again. And we'll assign some, we'll ask a few questions. We're gonna go by rotation, just like previous classes. Is Seni here? Seni? Mr. Seni.
Yeah.
Seni, looking at this circuit, at which part of the half cycle, at which part of the input waveform will the diode be on? Positive half cycle or negative half cycle?
Negative.
Negative half cycle. His answer is correct. You can see the diode is upside down, so it's reverse bias actually. In the negative half cycle, the diode will be on. The next student, Sipo. When the diode is on, which means during the negative half cycle, what is the output voltage that you will get when the diode is on? V out, VO or V out, how much would that be?
Just a moment, sir.
Okay. Let me short the diode for you. Negative half cycle, the diode is short. I did not say it is a silicon, so this voltage is 0.
Oh,
Okay, what is the voltage now?
should be in 25. Oh, no, sorry.
How are you measuring the output voltage? Your probe is here. V out probe plus and ground is here. You are measuring the parallel node. What voltage will you get?
Oh, parallel one. Give me a second, Nazan. Uh, 15.
15?
Yes.
Where is the another 10 volt? Someone wants to help him. What is the V out during the negative half cycle?
25 is correct?
No, 25, I'm afraid it's not correct either. If you look at the parallel node, this voltage shows across R, which is you are measuring. What do you see?
35.
Say again.
35.
35?
Yes.
I don't think so.
I think it's 5.
It is 5 volts. V out during the negative half cycle is 5 volts. During the negative half cycle, this branch is active. Did you not take the basic circuit course or physics lab 2? How do you measure parallel voltages? 5 volt will show across R, which is also V out, 5 volt. Okay. Now, who was next one? Mr. V2. Present?
Yeah.
We have to establish the capacitor voltage during the negative half cycle when the diode is on. So let me put the proper polarity, plus minus. The current is now flowing like this, counterclockwise. Can you find out the value of V sub C, the capacitor voltage. And also look at the input waveform. It is not symmetrical. Positive peak has one value, the negative peak has a different value. What is VC? Using the KVL, what is VC? What will be the equation? Okay, I'm going to move on to the next one. San An,
Yes.
what will be the value of the capacitor voltage?
Um, it be 20.
Input is 20. So if you take this sign, 20 plus 5 minus VC equals 0. What is VC? $25. Waramet? Is Waramet here? No? Is Waramet here? How about Nava 1?
Oh, yes.
Now come back to the positive half cycle to analyze. In the positive half cycle, diode is open. The current will flow through the outer loop. Tell me what is V out during the positive half cycle.
Give me a second, please.
Okay.
35 volt.
35 volt, correct answer. 10, so Vi plus Vc minus V out equals 0. Vi is 10 plus 25 minus V out, which brings us to V out as plus 35 volt. So V out for the positive half cycle is 35 volt. This is what we have established. Now let's look at the swing. We have to draw the output voltage swing. Positive half cycle, we found the value is, extend this axis a bit. This one is 35. Negative half cycle, how much was the voltage? Plus 5. So something like this. Not drawn to scale, but I believe you get the idea. 35 volts, and here is, this level is 5. What is the total swing of the output? Measure the total swing of the output. How much is the total swing?
30.
Yeah, from 5 to 35, you go 30 units. That's the swing. Your minimum value is 5, maximum is 35. 30 is the total swing. How about the total swing of the input waveform? How much do you see from this diagram? 10 times.
Also 30.
Yeah, 10 times above 0 and 20 units below 0. So total of 30 volts. Total voltage swing for input and output have also been satisfied. So you solved your problems. Sometimes there are problems if you see on your textbook. The input is given, the output is also given. You are asked to design the circuit which will satisfy the input and output. That's another way of giving you clamper problems. In a regular problem, you're gonna get an input, a circuit, and then you are asked to draw and tell me the output. If you twist it, you're gonna get both the input and output, and then I ask you, now you design. I believe there is a design problem like this, perhaps also on your homework. I can remember, but in your homework assignment, there should be one clamper problem. We'll now move on to the next and one of the most important topics. This is the last subtopic of diode and diode applications. That's the Zener. Hopefully we can still have time after finishing the Zener, because I intend to show you an application of logic gates using diode and OR gates. Now we should all be back at the slide which says Zener diode. I think everybody can see. Let's view a full screen mode. Is the picture okay?
It's okay.
So Zener is not like the regular p-n junction diode. It is operating when it is reverse bias, as you can see from the diagram on the right. Symbol is slightly different. It's not a straight horizontal line or straight vertical. It's a curved Z or Z. You connect the Zener like this, upside down, but once it turns on, you read the voltage plus minus. This is quite, I know it's quite different, but this is the special case diode. Physically connected in reverse bias, but once it is on, the voltage you read is like this, plus minus V. What is V? There are different models of Zener diodes in the market. It depends on your need. Which one are you going to buy? If you are buying a 2-volt rating Zener diode, once it is on, it will show 2 volts across. But the Zener is not always on, or it is not always off. We have to determine first whether or not the Zener is on. A typical circuit is shown in the bottom. An input voltage, a series resistor, then you have a Zener diode, and you have a load resistor RL. VZ refers to the Zener voltage rating, which comes from the model, the spec sheet. You have to determine first whether or not VL greater than or equal to VZ. How are you going to find the VL from this circuit? What equation do we use? VL means this one, the voltage that appears across the load resistor RL. So VL has to be greater than or equal to Zener rating. Let's say this Zener is the model of 2-volt Zener diode. VL must be greater than or equal to 2 volt. How do we determine the VL? To determine the VL, you have to mentally remove this thing. Just imagine that VZ does not exist. If VZ does not exist, the Zener does not exist, what do you have? You have this single loop circuit. What's the equation for VL? Voltage divider. You must remember, what's the voltage divider equation? VI times RL divided by R plus RL. Do you remember now? If you don't, you should go back, review the circuit theory. It is needed in order to function well in this course. Has anyone heard of voltage divider before?
Yes, Sajed.
So this is the voltage divider equation, VI times RL divided by R plus RL. The values of resistor will be given. In a normal problem, VI will be given. So you can see what is the VL. If you saw that VL is 1.8 volt and the VZ rating is 2 volt, the zener will not be on. Therefore, the zener current is 0, only the outer loop is active. But let's say you found by calculation VL is 3 volt or 2 volt, which is, let's say VL is 3 volt or 5 volts. The zener is on. Once the zener is on, the zener voltage of 2 volt will be shown as VL. So the VL value will be locked at the value of zener voltage. It is not 5 volt. 5 volt is coming from your theoretical calculation when you mentally remove the zener from the circuit. After you do the theoretical calculation, if you determine the zener is on, the zener voltage will be the voltage of RL, not your theoretical value. Okay? So we have to do some analysis. Let's see. Before we do any problem, we have to do some explanation. There are a few things to consider. If your input resistor R is so large, there is a possibility that the current coming from the main supply is not enough. For large resistors, you will have small current. And also you see current coming at this node. According to the Kirchhoff's current law, some of it will have to go to the load, and then the other part, the other branch will go to zener as IZ. Now imagine if you have two large value for R, you already start with a small current which is further branching. And there is a current called IZK, the knee current. There's a minimum zener current that is needed in order to run the zener. So when you have a small current, IZ less than the zener knee current, you cannot turn on the zener. So the minimum load current in this case has to be given by IR minus IZK. You see what is the equation at this KCL node? IR equals IZ plus IL. Look at this equation. IR equals IZ plus IL. If you think of minimum zener current, IL is IR minus IZ. So you have to satisfy the condition for minimum load current, which is this. When will you get the minimum load current? If you think of Ohm's law, V equals IR, which means R equals V over I. If you take the zener voltage, when the zener is on, the voltage across the load resistor is same as Vz. If you divide the voltage by something minimum value, you're going to get the maximum RL. So you cannot just pick any value of RL. Yes, you need a minimum RL as well to turn on the zener. We'll come to that. But also there is a limit, upper limit of load resistor, which will ensure that you have a minimum load current. And when you have minimum load current, it is sufficient to turn on the zener. What happened? Now we talk about the other case. If the resistor R, the input or the series resistor R, is too small, what is going to happen? Lot of current can come. IR will be large. One portion of it will go to the load current, load resistor RL, and the other part will go to the zener branch. When the zener is on, it will go as IZ. The zener also has a maximum current rating, IZ max. The maximum current IZM, if you multiply by VZ, voltage multiplied by current, you're gonna get the power rating, and power maximum is the maximum zener current allowed multiplied by the rated voltage. If R is too small, there is a risk that you actually are trying to flow more current than the zener can handle. That is a dangerous situation. You might damage the zener. So there has to be a maximum load current because IR equals IZ plus IL. The load current also has to be limited. If you take the load voltage divided by the load resistor, the load voltage now will be Vz, assuming the zener is operating. If you divide something by minimum, you're going to get the maximum. So IL maximum is the voltage divided by minimum RL. As you can see, there are two considerations for your load resistor then. You can go to a maximum point, but at the same time, you have to start at the minimum value of RL. Within this range of the load resistor, the zener will be on. Below this RL, the zener will not be on. Above this RL, the zener may not be on too because of the minimum zener current required. So what is the value? The minimum resistance value RL is this. RVZ divided by VI minus VZ. Where does it come from? It came from the voltage divider equation. VL equals the voltage across the load resistor, VI times RL, R over divided by R plus RL. So for minimum RL, if you take RL as RL minimum, you rearrange the equation, you will get R times VZ divided by VI minus VZ. We'll do at least two problems for two different cases. Any questions? Any questions?
No, sir.
Okay, it looks a bit complicated. That's why there are three different types of problem in the textbook to solve. For which, first, I'm going to bring you to example 227. Let me make this ready on your screen. Or no, 226. Start with 2 dash or 2.26. This is the most simple case of the zener diode. And in a few moments, I will switch the screen. Should be now in front of your screen, example 226. Can everyone see?
Yes, sir.
Okay, let me enlarge the diagram a bit. First, just look at this circuit. Input voltage 16, input resistor 1 kilo ohm. The VZ rating is 10 volt, which means if the zener is on, it will establish a 10 volt value. The maximum power allowed for this zener is 30 milliwatts. RL is 1.2 kilo ohm. First of all, ask you some questions. Let me write what we need to find. On the right hand side of the screen, I want you to find VL, VR, IZ, and the power output or power consumption of the zener PZ given this circuit. What is the VL? First, you need to determine if the zener is on or off. So let's determine if the zener is on or off. Mr. Natapok.
Yes.
Natap,
Yes, Ajahn.
can you determine the VL? What step do you have to take? First, imagine the zener is not there and tell me what is the VL. Or you can tell me the VL equation.
Just a moment.
Okay.
Ajahn, 8.73.
8.73. It's already
Yes.
done in the book, maybe you're looking, but how do you find out? VI times RL divided by R plus RL. You take 16 multiplied by 1200 and then divide by 2200. It is 8.73 volts. BL is 8.73.
Yes.
Let us write it down here. The zener is on or off? The next question is for Mr. Warapat.
Yes, Sajed.
The zener is on. About Miss Nataya.
Oh, okay.
If I ask you, Miss Nataya, is the zener on or off? The zener rating is given here. I'm highlighting in green. On or off? The zener is off. It is the VL you calculated from the theory is not equal or more than VZ. VZ is off. If VZ is off, there is no current IZ. IZ will be 0. If there is no current, it is not consuming any power because P equals VI. I is 0. VZ is also 0. Miss Pichayapon,
Yes, sir.
can you find VR now? Given the circuit, you establish there is no zener that is on. So what is VR?
VI minus VL.
VR minus VL, yes. It will be 10 minus, 16 minus 8.73, which comes to 7.27 volts. VI minus VL is the correct solution, 7.27. So now we will repeat this whole thing. I just create a partition here. Repeat the whole thing now. RL is 3 kilo ohm. I write it down, 3k ohm. Mr. Kumchan, please
Yes.
tell me now how much is VL in this case after you have finished analyzing. What is the calculated VL?
After RL changed to 3 kilo ohms, right?
Yes.
Um, I need to calculate it a bit.
You have to use the voltage divider equation to calculate.
Yes. Give me a moment.
Okay. Sixteen times 3k divided by 4k.
Is it 12, sir?
So
12
calculated is 12.
volts. Yes.
You calculated, is it greater than or equal to VZ?
It is greater, so
It is greater,
the
so VZ is on.
zener is on. Yes.
Once the zener is on, what will be the VL then?
10 volts.
So final VL, I should write here VL calculated, VL calc, so that you are not confused. Calculated value. So final VL will be 10 volts. Well, that's right, correct. So you see there needs to be a minimum value of resistor. Let's find VR. What will be VR? The VR will be solved by Mr. Piradon. Are you here? Piradon.
Yes, I'm here.
Okay, tell me what is VR now.
Sorry, teacher.
VR, the voltage across the first resistor, how much is it? Now the diode is on.
Is it 16?
Okay, the voltage across is shown here. The loop, you can take the left loop or you can even take the outer loop. So in the loop, if you apply KVL, how much you get for VR? The Zener is right now on. So I put the Zener polarity too. I'm gonna move on to the next student, Mr. Kitsanapong.
Yes, teacher.
What is VR?
Sorry, I still don't understand it yet.
VR, look at the loop. VI minus VR minus VL equals 0. So what is VR? You already established VL is 10, VI is 16, so VR has to be 6 volts. The total
Okay.
voltage in the loop is 0. Next question, what is IZ? IZ, Atit, can you tell me what is
Yes.
IZ?
Yes.
Here is the current coming in. IZ, you can say IR equals IZ plus IL. Therefore, IZ has to be what? IR minus IL. Can you find IR? We already know what is VR, and we know the R. While you are trying to figure out, IR is VR over R. Yes, say
6 IR 16 minus
6 volt.
oh,
IR
6
is
volt. Yes.
6 volt divided by 1 kilo ohm. Which means 6 milliampere.
Yes.
6 milliamp. What is IL? Again, use Ohm's law. BL divided by RL. 10 volt divided by 3 kilo ohm. So you get 3.33 milliamp. 3.33 milliamp.
2.67.
So the final value for IZ is 2.67 milliamp. The last question for this Tasin, you are the next person. What is the power consumption PZ when the Zener is on? What power is being dissipated by the Zener now that it's turned on?
$26.7 millivolt.
Yes. PZ is the product of your Zener voltage, rated Zener voltage, and multiplied by IZ. If you take 10 volt multiplied by that value, 2.67 milliamp, you're gonna get 26.7 milliwatts. Is it safe Is the condition safe? Yes. Look at the rating. From the circuit, you can see maximum rating is 30 milliwatts. This is almost 27 milliwatts, but still safe range. We have not exceeded the Zener power rating. So this is okay. The next problem, the workout example that we will be looking at, is a fixed value of input voltage, but the load resistor will be variable. We have already seen the theory on the slide that you need to have the RL in between a range. There's a minimum RL and then there's a maximum RL. You cannot go beyond this range. So with minimum RL, you have maximum load current. With the maximum RL, you have minimum load current, which we will see in the next example now. Again, let me enlarge the picture. Determine the range of RL and IL. That will result in the V load resistor being maintained at 10 volt, which means you need to keep the Zener on. That's the meaning of this thing. What is RL mean? RL minimum. If you go to the equation, if I tell you directly, I remember it's R times Vz divided by Vi minus Vz. So RL minimum, how much is RL minimum? R is given, Vz rating is given. This is the equation. If you don't remember, you don't have to stress, because you can actually use the voltage divider equation. Vz equals VL equals Vi RL over R plus RL. You rearrange, you're gonna get this equation for sure. So this is minimum RL required. How much? 10 times 1000, which is 1 kilo ohm, divided by Vi is 50 and Vz is 10. 10,000 divided by 40, we get 250 ohm, the minimum RL. If you have minimum RL, you can also get, I think, maximum IL, right? What is maximum IL when the Zener is on? IL max. After Tasin, I have Sukaina. IL max. Sukaina, what is IL max?
Just a minute, teacher.
Okay.
Is it 1.25?
I have a lot of background noise from you. You can turn off. Please turn off your mic. The maximum load current is the load voltage divided by minimum load resistor, which we find out. So once the Zener is turned on, the load voltage will be 10 volts, 10 V, divided by the minimum resistance you need to turn on is 250 ohm. I think, how much is it? 10 divided by 250 is 0.040 milliamps. 40 milliamps. Now we have to find the remaining parameters. We need to find RL max and IL minimum. To do that, we have to find other parameters like IR, IZ, etc. So how do we find IR? It is V over R. We don't know VR yet. your first step is to find VR, which is VI minus VZ. VI minus VZ, how much would that be? 50 minus 10, 40 volts. 40 volts is VR. IR, Sirin, is Sirin here?
Yes, Ajahn.
Sirin, what should be the value of IR in this case? What is IR?
40, Ajahn.
40, what's the unit?
40 MA.
Small m, milliamp. 40 milliamp, don't forget the units. Now, what other information is given? IZM, maximum Zener current. So IR is coming to this node if, and then at this node, Zener current flows away, load current flows away. If you see the equation, IR equals IZ plus IL. We established IR is a fixed value. If the Zener current is maximum, which means the load current will be minimum. If this guy takes away all the current, the load will be the minimum load current. You can also say, rearrange the equation. IL, if you want the minimum IL, we already established maximum IL. If you want the minimum IL, from IR you have to subtract what? The maximum possible Zener current. IZ max is given. What is it? You have IR 40 milliamp, IZ max is 32 milliamp right here. So minimum load current that will keep the diode on is 8 milliamp, 40 minus 32. Once you have minimum load current, you can find the maximum load resistor. What is maximum load resistor? This question will be for, I have Hin Min in this class, is that correct? Are you in this class? No. There is no new student. Okay, I got confused with a different class then. Balan, first person again on the list.
Sir.
Balan, what
Yeah.
is the maximum RL then?
Uh,
What will be the maximum RL?
uh, 72.
What is the equation for RL? Can you tell me the equation for RL? What is the equation for RL?
Wait a minute.
We'll wait for a few moments.
Yes. I that.
RL equals RL maximum. Have you forgotten Ohm's law?
Yeah.
Thirawut? Thirawut,
Ajahn.
can you help him? What is RL max?
Can we use the VZ divided by IL min?
Absolutely. That is, Vz will be the load voltage when the zener is on. You divide it by the minimum current, it will give you the maximum. You divide something by minimum, you're going to get the maximum. This is IL minimum. That's the only way to find out RL max. So what's the value? Vz rating 10 volts. 10 volt divided by 8 milliampere. What is the final value? .25 kilo ohm. 1.25 kilo ohm. I want you to practice these problems again at home. You don't have to submit, but you have to practice to see how to solve. So minimum you need 250 ohm, and the maximum RL will be 1.25 kilo ohm. If you try to increase more, it will not work. If you go below 250 ohm, it will not work. This is a variable resistor symbol right here. The arrow on RL, it says a variable resistor. You can be between 250 and 1.25 kilo ohm. 250 ohm, 1.25 kilo ohm. Not outside of this range. Outside of this range, the zener will not turn on. There's another example, example 2-28. I would like you to practice that one at home first. If you still don't understand, we'll do again during a review class. But I did not teach this one in the last semester. This semester, I intend to teach you something else, which is also part of the diode chapter. It is AND OR gate, logic gates using diode. Are you familiar with Boolean logic?
Yes.
Okay, so you can use diode and other amplifier and create logic gates. Let me write the topic, diode logic gate. And then I would like to bring some examples. Give me a few moments. Instead of me drawing, I think just bringing in the picture is better. It's quicker. Okay. This one, I have a picture that I can actually select and copy. Edit. How do I select? Okay, I have to take a snapshot, I think. Okay, and the picture will be here soon. So it is being brought in. Takes a few moments. Here are two diodes. You have logic and then you have logic OR. This seems to me like a logic OR gate. And then you have OR. If you are given a truth table, for Boolean, 1 is high or on and 0 is low or off. If you want to get an output, say you have 0 and 0, 0 and 0, the AND gate result will be 0. 0 and 1, 0. If you have 1 and 0, means the first one is on, the second one is off. You also get the output as 0. When both are on, the AND gate will be 1 output. For the OR truth table, it works differently. Only one of them has to be 0, only one of them has to be 1. So if you get both zeros, you have 0. 0 or 1, the output will be 1, high. 1 or 0, the output is 1. And obviously, when both inputs are 1, you still get a high output. That's the logic, Boolean logic. Now look at these two diodes. The first diode, silicon diode, second diode, silicon diode. So it's like this. Because of the symbol, I can say it is anode left and cathode on the negative side. This ground level is 0 volts. What is the status of diode number 1? Is it on or off? Can you tell me what is the status of diode number 1? On or off?
On.
The diode 1 is on. 10 volt is more than enough to turn it on. Once it is turned on, you have 0.7 volts. Let's look at the second diode. You have 0 on anode, and also on the ground it looks like 0. Is it on or off?
Off.
Off, open circuit, no current flows. So now your voltage probe, the voltmeter probe, is at this point. It is sensing the volt. If you try to find the exact voltage value, analog value, what will this be? The bottom loop is open loop. The top loop is a closed loop. The book has redrawn the loop, which I will also bring in now as a snapshot. So I copied something, and then let me paste at the bottom. If you redraw the circuit should look like what is about to come up on your screen. Increase, okay? So the second diode, the one that was off, it is like this. The second diode is right here. 0, and then connecting to the right hand side, open switch, nothing flows. The first diode, meanwhile, you gave a plus 10 volts, so we can draw a battery symbol, plus here. The minus is the ground of the battery, and the rest is connected to the rest of the circuit. So the outer loop is active. Now you want to put a probe. VO is the voltage drop from beginning all the way to here. 10 minus VK. VK is the diode on volt, 0.7. 10 minus 0.7, it's a 9.3 volt. A 9.3 volt is considered a high level for Boolean logic. There's something called a transistor logic, which is not part of this course, but 9.3 volt is high enough to be considered level 1. So you have a high output. What AND logic does it represent? It represents the third AND logic, OR logic. This is an OR gate. 1 or 0. Any of them is on, you will still get a high output here. The first one was on, second one was off, but you are sensing a high voltage. This is the third OR logic. If the both inputs were 10 volt, how much will you get? The second diode, if I turn it on, how much will you get? At that point, at exact the same point, you will still get 9.3. You can analyze 10 minus 0.7 here, and this is also a parallel node. 10 minus 0.7, you still get a 9.3, which represents 1 or 1. The output is a high. In this case, the high level is 9.3 volts. If both diodes were given 0 volt, what will be the output?
0 volt.
0. There will not be any output. It is a Boolean logic 0, logic low. Maybe we have one more example here, 2.15. I'm just trying to see if we have it here. Using a slightly different arrangement, how come I don't see it? Because it was not taught in the last semester, that's why. So let me bring in example 2.15. Give me a few moments. I'll take a snapshot from the text, and the next thing I'll do is create a new page. And then copy paste the picture. So give it a few moments. Okay, it's right here now on the screen. We have to look at each diode and see, try to sense. So when you see two diodes with different polarities, in general, the best approach is to simply establish, first you can establish a gut feeling, like how do you feel for the state of that diode. Look at the different polarity and different side in terms of pressure. Which one is more positive, which one is more negative, which one is more on than the other one. You can also think, if you have two inputs, compare which one is more positive and which one is more negative, and then you determine the on-off state. The easiest approach for this particular problem is, I see a path established from the bottom, so let me look at the bottom part of the circuit. Look at the voltage that's coming in and look at the orientation of D2. Is it on or off? So D2 polarity is like this, anode, cathode on the left. Is it, do you think it's forward biased?
Yes.
Yeah, because the current is plus minus, it will flow counterclockwise, so it will go like this, and this side is 0. We can draw the ground, so we have a loop, common ground. The left and right ground is a common ground. Diode D2 is on. What about diode D1? Diode D1 is going to get the voltage V out that is fed into this side. Polarity again, here is anode, that side is cathode, and then you see a positive volt. You are not normally expecting positive on the cathode. It has to be negative, right? My feeling first is this one is getting a positive volt 10, which is not a forward bias because you are putting positive 10 with the cathode, and then this one is having a much less than 10 volt. We can solve for the bottom loop. So when the current flows counterclockwise, the polarity of the resistor becomes like this, plus minus, because current flows from plus to minus. Battery is going plus to minus, which is the ground. I'll say the D1 is off. D1 is totally off. Switch is open. D2 is on. So what is V out? If you put the probe V out at this point, what is V out? You can solve for the loop, the left-hand loop. 10 minus VR minus 0.7 equals 0. We can find VR. What is that? Ten minus VR minus 0.7, which means VR equals 9.3. The magnitude here is 9.3 volts. 9.3 volts. So what is V out then? V out you can see as from two perspectives. The probe is actually sensing this one. Or you can also sense this one from top of the node to the bottom. If you take minus 9.3 plus 10, how much do you get? 0.7. 0.7 volts here. Is it 0 volt? No, it's not 0 volt. Is it, even though it's not 0 volt, but 0.7 is not high enough for the Boolean logic to consider. It is rather low for Boolean logic level 0. So Boolean output will be 0. You see, one diode is on, the other one is off. If the combination of 1 and 0 gives you a logic 0, what type of gate is this? One or 0, you will get a high Boolean output. 1 and 0, you finally get a low Boolean output. So this gate is an AND gate. The previous example was the example of OR gate. Either one turns out, you'll get a high output. Now, if you have one of them on, the other one is off, and the final is equivalent to a Boolean 0, this is the AND gate. Any questions?
How we can know is and or on or again?
Sorry, say again.
How we can know is and or again?
You have to compare the situation with the truth table. Maybe you have not taken the course yet. Some students, they took digital logic or they will take. So see, this is the truth table. It is called a truth table, the one I did previously. When any of them is on but the output is low, this is the AND gate. In that example, the first diode is off, second diode is on, but when we are measuring V out, we calculated it is 0.7. It's rather low volt. At least for logic high, I think you need more than 1 or more than 0.8. I'm talking about a different subject. But if one of them is off, the other one is on, and then at the output you get a high level, that belongs to the OR logic gate. This one is an OR gate. This, because of the circuit design, this one became OR gate. And the second example that I showed to you, it's AND gate. There are other logics, NOT gate, XOR, but the two main things you remember is only the OR gate and AND gate. Where was I? Collaboration. this one. 1, 0, but the output is still 0. So this is an AND gate. There are more problems like this. I remember in your chapter, not the example, but exercise at the end of chapter, problem number 18 and problem number 20. These problems are quite good to practice.
So this one V out equal to 0, right?
Yes, because we found that using the KVL loop, the value of V out, the analog value is 0.7. Even though it's not high, but for Boolean logic, 0.7, even though it's not 0, 0.7 is not 0 for analog. But for digital, for Boolean logic, it is still a low level. Most transistors will not recognize high voltage if it does not pass 0.8 or 0.9 volt. So Boolean logic, according to digital logic, it is zero logic output. So this is an AND gate.
Ajahn, so if the outcome, the VL is more than 1, then it can be OR, right?
Yes. If you have more than 1 volt, which is considerably high for Boolean, then you can say, okay, only one of them is on, the other one is off, but we have a high output instead of AND, this will represent the OR gate. Maybe we can increase the DC bias here. Instead of 10 volt, I can just increase by only 1 volt. Maybe 10.5, or if I put 10.5 volt, the total scenario is going to change. If I put 11 volt, even better. So at 10 volt, it is still not enough for Boolean high. It is the Boolean low. I guess that concludes our lecture. There was one more slide left. Let me go back to the slide and see what we have been missing. The last slide, then I'll go to your attendance call. The last slide was slide number 58. What are the practical applications? So rectifier circuit, you have seen full wave and half wave rectifiers. Conversion of AC to DC voltage, that is done by rectifier. In battery charging circuit, you can use diode. Simple diode circuit can be used for so many things. You can protect from overcurrent, reverse polarity, and Zener circuits are quite useful. You can protect from excessive voltage. You can also set a reference voltage for the rest or a certain part of your circuit using the Zener rated voltage. On Thursday, which is our next class, we'll begin the chapter of BJT. Now let me take your attendance. Balang, here.
Yes, sir. Yeah.
Kiravut, Napatra,
Yes.
Akon,
Yes.
Rajay,
Yes, Ajahn.
Jonikan,
Yes,ค่ะ.
Michelle, Phil.
Here, John.
Okay, Phil is here. And then Silicon.
Yes.
Today, I don't think Michelle is here today. Silicon is here, I heard, and then Wisalut,
Yes, Captain.
Yuchen,
Yes, teacher.
Sheshehan,
Yes, Ajahn.
Patompong,
อย่าครับ
Pungsu,
Yes, sir.
Martin,
Yes, Ajahn.
Korawit, Mr. Korawit, Pichayut, is Pichayut here?
Yes, present, Cap.
Jimma,
Yes, sir.
Chuan Yuan,
Yes, Ajahn.
Sattawat,
Yes, Ajahn.
Yapeng. Yapeng.
Yes, teacher.
Okay, Seni,
Yes, I'm here.
Siripok,
Yes, Ajahn.
P2,
Yes, Ajahn.
San An,
Yes.
Waramet, I don't seem to see Waramet. Waramet here. 1 second. No, he's not here. Nabawan,
Yes, I'm here.
Nathapok,
Yes, I'm here.
Warapat,
Present Ajahn.
Nattaya,
Yes, teacher.
Pichayapon,
Yes, sir.
Komchan,
Yes, sir, I'm here.
Iradon,
Yes, I'm here.
Itsanapon,
Yes, I'm here.
Atik is here, Tasin is also here, Sukaina is here, and Sirin is here. One more check for Michelle. Is Michelle here? No. Michelle and Boramet are not here. See you on Thursday. The class is now dismissed.
Thank you, John.
Thank you, sir.
Thank you, Ajahn.
Don't forget your homework due next week.